Okay, so we'll see how long this video is. Essentially, in the last video, when I talked about the different properties of black holes, gamma ray bursts, accretion disks, ergospheres, photospheres, firewalls, event horizons, it left me thinking about the idea of VSL black holes and the whole fractal dimensional idea I had originally. When I started to realize that these things called ergodic graphs can actually be modeled every single time like sphere packing. Kind of here was when the first time I kind of saw it, and I tried to compare it to light cones and VSL, but really they're like 4D manifolds, so it's not the same. It's like they're really like 6-dimensional light cones, which is pretty cool. Okay, so I'll kind of go straight to it. If you know, in sacred geometry, they talk about Metatron's cube, and all of these, they're all basically based off of sphere packing. So in sphere packing, you're allowed to put as many circles or spheres together as possible where they're not overlapping. In the case of this diagram here, I did as many possible overlaps on this one. So the way I thought of them was there's overlaps and there's embedding, and then there's kind of encircling. I didn't write that one down, but you can think of this outer one as encircling, these as overlapping, and these as embedding. So you can keep going deeper and deeper into a fractal, zoom in or out. You can overlap in 2, 3, or 4. So these are 2 overlaps. They will only overlap 2 circles. These red ones are 3 overlaps. And then these orange ones are 4 overlaps. So you can kind of see them. The orange ones kind of match in this diagram what would be, I believe, the second one. So what would be these embedded inside. So you actually don't see the original embedded. I added them in these orange ones, but in the original blue. And then, so these central ones are examples of 2 overlaps on the inside. So you're either gonna have an overlap of 2, 3, or 4, an embedded. So it's gonna have the 6 in terms of 2 dimensions, or the encircling. So you can imagine many of these. And so my idea that I kind of sent to you was you could have many of these, and they can be facing this way in and out in 3 dimensions in a 3-dimensional lattice. They could be rotating in hyperchirality, every single one of these spheres. And they can also be, there could be like a Laplacian gradient, basically talking about the divergence or convergence of any of these spheres collectively as they are within their symmetry groups. So let me go back to the idea of the ergodic graph. So there's these things called Markov chains, which actually come from computer science, which is this thing that you can have a state represented by a point, and you can have how many ways there are to get from any state in the system to any other state. So if it's one point, it's really easy. You can get to that state from itself. Whatever operation you did, you can reverse it. So the 2 arrows going this way and that way. If you have 2 points, you can go from one state to the other, or back, or you can go to that state in a different way, or back, or from this way back. You can go from that state to itself, back. You can go from that state to itself and back. When you have 3, you get this thing, same idea. You can go from one state to any other and back. Once you get to 4, it gets complicated because you have to cross through the center to that 4th one. You can't see it because I didn't do it 4. I just skipped straight to 6. So in this one you see it, there's 6, and then you'd have to skip to the central ones. And so essentially there should be a way to describe this as simply as possible using the internal sphere coverings. If you see like this one as an encircling of another sphere that would end up over here, that would correspond to one of these arcs so it would go off the graph. And then these self-referential states, paths on the graph, on the Markov decision graph, or ergodic graph, would be like spheres. So they'd be like the spheres, if these were equal sized, that would be like embedded in a larger circle or sphere. This is just a two-dimensional version, but you could do a three-dimensional version as well, where there were spheres. And so you get these simplified versions where there's two states. It actually becomes three spheres or three circles. One state is a single circle. Three states would be four, etc. like that. So the point of that was, in terms of this graph, you can think of each of these points on this graph as a three-dimensional space. Every single circle as a four-dimensional plane. It's really a manifold representing a four-dimensional space. And then any kind of shift in that, what I call fractal continuum, within that four-dimensional space to five-dimensional space. So that'd be ADS space. And the best way to imagine that before I go to six-dimensional space is to think of black holes. So you're outside a black hole, you're over here, and you're looking at the surface of a black hole. It appears to be two-dimensional. It appears to converge infinitely. If you're inside a black hole, you're looking out, it'll look like it's four-dimensional and it diverges infinitely, and you're still going to seem to be in conformal stereographic three-dimensional space. So whether you're outside or inside, but in actuality, you're still inside another black hole, and this one has these other observers outside that will say the same about this outside the black hole appearing to be two-dimensional. So the point is that this entire space is really like a higher six-dimensional projective space, and then the complex space that appears as fractal basins in 2 dimensions to us, it's actually representing a higher 5-dimensional ADS space. So stereographic projective relativistic space will always appear hyperbolic. And so this fractal continuum, which I could just keep drawing more event horizon diagrams this way and this way infinitely, is like this. It's just embedded circles in this case, but you can think of them as spheres. And the ratio is actually dependent on the way you can embed them without there being overlapping. But these light cones representing these states actually allow for overlapping, because this is an imaginary time. So just like the idea of the twistors from the firewall, which expand the space from the firewall to the event horizon, have this proper time and that are producing the entanglement entropies for the ADS space, defining their divergence and convergence. In actuality, this takes an infinite amount of time, so it's really an imaginary instant in which you're defined in stereographic space. But within this time, it all happens simultaneously to the light itself, to the twister's perspective. So this entire space happens simultaneously as well. And so you can think of looking at it from this perspective. You can just keep drawing spheres, and eventually you'd get something like this. So that'd be the front facing of many of these 6-dimensional light cones. And this is the simplified version of the graph, where I'm just explaining this direction as kind of an antimatter system of light cones, and this direction as a regular matter. So they're both converging to infinity. And then this entire space is imaginary time. And then you can think of this fractal continuum as a VSL cardinality. So the smaller you go, the smaller the cardinality, and then the higher the larger. And that just determines how fast information is processing. And so if you actually look at the Birkenstein limit video that or not video, research paper that you sent me, it kind of looked like one ring of these. So if you're in a smaller ring or a larger ring, then the information transfer will differ. Fundamentally, it'll be greater in the larger universe, but for relativistic reasons, it'll be faster in the smaller, something along those lines. So we don't really have the mathematics for yet, but that's why I was studying algebraic topology, just to give you a quick look. I was studying this fractal geometry book by Kenneth Falconer, Topology, Bert Mendelsohn. These are all the Dover introduction books. Graph Theory, Trudeau, and Fourier Series by Tolstov. Those are just fundamental books that I was just looking over. So I'm still looking over those. What I was thinking is the dynamic evolution of an Apollonian sphere packing graph. So if you were able to kind of take this, each of these slices is a four-dimensional space, remember? It's the entire possible evolution of a universe. So when they give you the traditional light cone, like this is our universe and this is an antimatter universe, this entire space is like one slice in this graph. And so because of that, the actual matter in this universe also packs fractally. It's a stereographic projection of this six-dimensional, this is like the front face of it, onto our three-dimensional correlate, stereographic correlate. And so you can model that as Apollonian sphere packing. And then it would have these kinds of divergences of their gradients, or convergences of their gradients, which would depend on the zeta function representing our local real solutions of this fractal basin complex projective space that's within the Planck space of the event horizon. So you guys kind of have to study algebraic topology and look at these weird graphs that kind of tell you, outside of actually studying the algebras of fractal geometry, to tell you things about quantum gravity, which are kind of understood right now in terms of low energy, like large scales low energy, but not in terms of small scales high energy. And so that would require you to provide solutions from this six-dimensional ergodic space. And so basically I'm saying it's ergodic because there's a path, just like in these graphs, from any possible space in this complex projective space to any of the real solutions inside any point and anywhere in this graph. So any point that you put anywhere has a corresponding circle, which is a four-dimensional space, and a corresponding light cone. And the reason that you can pick any point is because as you go fractally into this structure, so you put spheres inside spheres, or circles inside circles in this case, for this one you'd get this shape inside every one of these circles, and that shape inside every one of those circles, and it would just become incredibly detailed to the point that it would just fill the entire space. And so that goes back to the idea of the Hilbert curve and filling up the entire space. So this is probably something like a Hilbert curve. And it's also a lot like the neocortex paper from that Reed college neuroscience paper on how the neocortex evolves as a fractal, or those 3D modeling videos from I think it was a mathologer, but that other math YouTube channel that they have these mathematicians who model fractals in 3D, and then they show as they evolve in one direction with more iterations in that direction, they become more detailed. So the thing is that because this would be infinitely convergently fractal and divergently fractal, so the way I think of it is it would keep expanding outward, and you could zoom in on one of these and it would have its pattern inside, and you could zoom on one of those circles and it had the pattern inside, and you could keep doing that, so you could zoom in and out. It wouldn't look different at any stage in terms of the space. But in terms of an imaginary instant in the stereographic projective space, when you're inside one of these black holes, as we are right now, you might get some subsymmetry of it. It might look something like this, I don't know. So there might be less dense matter and more dense matter, and that's a local asymmetry that kind of represents a lot of what modern physics is right now, which is finding out why gauge symmetries are broken at electroweak phase transition after the Big Bang and everything, which really is most people don't think of it as a Big Bang. I think of it kind of as Valencian tunneling from the singularities in this ADS space, which are really just entanglement reference frames from the entanglement entropy of these twisters that are entangled to different Planck spaces on the surface, which the Planck space is really just a simplicial complex between three of these spheres in a specific entanglement reference frame, which now we know what that kind of means. It's like this network of these embedded spheres, n-dimensional spheres. Really, in this space, they're 5-dimensional spheres. Right now, we're just looking at them as 2-dimensional circles. And so that would kind of tell you why we see local asymmetries, and why it's even possible to have a kind of fractal universe. But because that is a local property, there's a cohomology between the 3D stereographic space and the complex projective space, obviously. So these cohomologies I've talked about before, I call them Huerta puzzles, has to do with the various fractal basins and how they're entangled. They become resolved in this larger ergodic graph by the fact that every state is connected to every other state. And so a lot of theoreticians in physics are against the idea of an ergodic universe, but I agree with that. It's impossible to have an ergodic universe, but it's necessary to have an ergodic multiverse. Yeah, and I didn't talk about error correcting codes, but I think that has a lot to do with once you go into the higher dimensional correlates, thinking of these things as spheres, and fractally, you're going to have some areas, if you had many of these, for example, next to each other, some areas within these fractal basins that are evolving differently. So they're pushing, they're diverging, and that might force a different area to have a convergence factor that varies, and therefore the total symmetry of the group is a lot like the Penrose triangle, and locally possible, but cohomologically the global properties are impossible. All right. And so error code correcting has a lot to do with the Fibonacci flower method. Once you correlate that to a higher dimensional perspective, it has to do with the fact that, well, if this sphere is diverging larger than this one, or this one's converging faster, you're going, instead of getting a perfect circle in terms of the encircling property, you're going to get some kind of spiral, and that's going to have a chiral property of invariant time symmetry to some other fractal basin that preserves the total global symmetry. So that's how they kind of resolve the cohomology. So I think this, as we know, just not thinking of it algebraically, numbers represent geometrical relationships. So really what we're talking about with this is what are the transcendental numbers, which is harder to explain. I'll try next time. We know that in this space we have the complex numbers, and then you can think of the overlapping as the rational numbers, and then you have real solutions in the stereographic space, which represent the rational numbers but are in a specific plane. So they're not just in one circle, but they're like in a plane. And then you have probably the natural numbers, which you can think of as just within this 4-dimensional space, they're points, so they're kind of like points of symmetry in terms of the sphere packing in that space. So it'd be something like the positions of atoms or something like that. Let's see if I missed anything. Of course, as I said the last time, I think that's Valencian tunneling and happens from that entanglement entropy, and I think that actually happens from Kugelblitz black holes forming, which actually end up creating these patterns. So in ADS space, the Planck frequency twisters from the firewall would be creating these Kugelblitz black holes. And I just kind of extrapolated that from the amount of energy it would take to to make a Kugelblitz black hole, and the fact that it's impossible to do it with lasers for humans, no matter how much energy we extract, because of the amount of space you would have to condense it into. Which also tells us about the evolution of surface complexity and surface entropy of the black hole, and temperature as it decreases, temperature increases, which is probably preserving the complexity. It's probably a complexity preserving process. Yeah, I just kind of wrote this equation. I haven't said enough, just generally about the divergence of the gradients. It's probably some function of these zeta functions. I'll probably make an index for however they're produced and whatever set. But yeah, I don't know enough mathematics for that. And yeah, so that should be it.